Okay, now we're going to start talking about those pesky energy levels that many of you were asking about after your first chemistry workbook lesson. So to understand energy levels, you need to have a basic understanding of the wave-particle duality of light, but very basic understanding. Just know that light travels like a wave, so it's able to bounce and refract or reflect around corners, and its amplitude tells you something about its energy as a wave. But light also emits energy in tiny packets that travel like particles. Sometimes they're called quanta, or photons is what you'll often hear them called, and that'll come up again in biology. The experiment responsible for our understanding of the particle nature of light involves shooting beams of light at metal and knocking electrons off the surface. And the crazy thing, the thing that no one expected, was that it was different colors of light, not different light intensities, that was changing the number of electrons that were getting knocked around. I'm not going to get into lots of details here, but this really only made sense to the physicists of the day if light was seen as a particle. So photons, that particle nature of light, depend on the frequency or the wavelength, which we tend to see as different colors in the visible light spectrum, not the amplitude, which is more like strength. Like when you think of a wave in the ocean, the taller the wave, the stronger it's going to hit you if you're out there in the ocean with the waves. Niels Bohr is the one that coined the term energy level to help explain why atoms only emit light in certain spectra or colors or wavelengths, depending on how you want to look at it. We knew that different elements were emitting these different spectra of light. So he hypothesized that since energy is released when objects fall, and the nucleus, the protons and the neutrons, were already stuck in the center, that maybe the electrons were somehow falling, quote unquote, between energy levels. And so they were emitting very specific wavelengths of light. And so he thought that these energy levels might be fixed, and the electrons were existing in one or another and falling between them very specifically, but the electrons couldn't be found in between. And so that's where our original notion of energy levels came from. So this is very much like a person lives on one floor of a building or another floor of a building, but there's no halfway point, because it is not energy efficient to constantly be, trying to jump off the ground so that you're existing in the middle of a room instead of on the floor of a room. And this Bohr model worked great for hydrogen. It did not work for any other elements. There were too many other factors at play, but he did lay the groundwork for our understanding of an atom using classical physics. He described electrons having ground states, so that's an electron that's occupying the lowest possible energy level, but they didn't fall into the nucleus. And that's important. They weren't revolving around and slowly spiraling into the nucleus. They existed at different levels. And so he was correct in that, in a sense. And then I also want to point out here, because you'll see this again also, that the electrons can give off energy as they're falling, and they're absorbing energy as they're becoming excited and bumping up a level. So classical physics was done explaining the atom. So quantum mechanics continued to investigate and describe the atom, or all those physicists using quantum mechanics. So we're moving from thinking of electrons in pretty orbits, very much like planets, to thinking of electrons in clouds where they could be found everywhere or anywhere at once. And so they're behaving more like waves, they're also behaving like particles, and you can get more information on all these crazy physics notions of an electron if you search the web for Colorado Physics Spectral Lines. They have some really good discussions on light emission and wave-particle duality if you want to go more into that. We're going to move on. But this is the beginning of our understanding of modern orbitals. And so I just want to point out that once you predict all the possible places you could find an electron, you take 90% of that density, and that's what we now call an orbital. So once you start thinking of electrons in a more wave-like way, you can think of them as clouds of possible placements, but they're too small to be measured. The measurement of an electron in and of itself would affect the measurement of electrons. So you can't measure the velocity or the placement or the position, and that all falls under the Heisenberg uncertainty principle. Again, something we could go into much more detail about, but we're not going to. And then Schrödinger, the same person responsible for Schrödinger's cat, also discovered that if electrons were going to be viewed as waves, we're going to have to represent them as integers. And so those integers became the basis for the quantum numbers, which I'm about to talk about. So what are the numbers? Well, n. Quantum number n is the principal quantum number. And so this is talking about how far away from the nucleus the shell extends, or the energy or the electrons extend. So there's your nucleus, you got some axes there, and then you would have shell number 1, shell number 2, shell number 3. So again, these are all positive integers, these quantum numbers. The next quantum number is lambda, and that's the sublevel. We're going to look at 3 sublevels: S, which is spherical, P, which is dumbbell-shaped, and D, which is more butterfly-shaped. There are others. There is F, for example, that comes after D. But these shapes just represent where we expect the electron density to be. They don't actually tell us where exactly the electron is. It helps us predict. Because, again, we can't measure something as small as an electron. We can't measure its velocity and its position at the same time. And then you have M of lambda, and that's the magnetic quantum number. And so this is telling you how, and you'll see this in just a second, how those sublevels or subshells are oriented in space. Because once you get past the S shell, they have different shapes and they can be oriented in different ways. So, if you're looking at S, you can see that there's only one possible orientation, it's a sphere, but you can see those shells, energy level 1, energy level 2, energy level 3. So this can get confusing because it's really easy to confuse this with an older version of an atomic model because it's very similar. The further you go out from the nucleus, the more energy those electrons have. So we're kind of building off of older models. Here's the P subshells. So you've got this first picture is just, again, showing you that electron density cloud, and then you have 3 different orientations given by that magnetic number, that magnetic quantum number. So you can have it oriented along the 3 different 3-dimensional axes. And then when you get to the D subshell, it gets really tricky. So that butterfly shape exists in 4 of the 5 possible orientations. But that's what your D subshells look like. And so let's keep talking about orbitals. So from here on out, when I use the word orbital, I'm going to be using it to describe the sublevels, S, P, D, and so on. And so an orbital is a place where there is a high likelihood of finding an electron. We're still looking at kind of stepwise increases in energy. We're still talking about orbitals, but the meaning of that word has changed. So what we're moving into now is a discussion of electron configurations. There's a ton of underlying science here, but I'm just going to ask you to accept a few assumptions. So here are the assumptions that just accept it. Assumption number 1, each orbital can only hold 2 electrons, but some energy levels have more than 1 orbital, so they can hold more than 2 electrons per energy level. Assumption number 2, When there are two electrons in one orbital, they're going to spin in different directions. And so we represent that spin as upspin or downspin with arrows. Assumption number 3. Every electron is represented by a different set of quantum numbers. So once you take the n, the lambda, and the magnetic number, and the spin, every electron has its own little set of numbers. And so this is also known as the Pauli exclusion principle, that electrons have to occupy different spaces in the atom. And assumption number 4, that everything in the universe seeks the lowest potential energy. I hinted at this before, that we're not always constantly jumping off the ground to exist in the center of a room. We rest on the floor of a room. And so do electrons. They rest in their lowest energy state. And so this is also known as the Aufbau principle. And so all of these electrons, with all of their interactions, eventually determine how the atom itself is going to behave. So your chem workbook talked about 2n squared, and I promised I would help you make sense of it. So here we go. First 3 energy levels are represented here. So you can see energy increasing with that arrow. They're also with their sublevels, the S, the P, and the D. So see, if I put 2 electrons in that first orbital, and then 2 in each of these orbitals, and 2 in each of these orbitals, those little lines, you get 2, 8, and 18. So that's where the 2n squared comes in. Now we're going to talk about where the 8 comes in just a second. So remember that S and P and D orbitals, like the fact that there's only one S, there's 3 spaces per P, and there's 5 spaces for the D. That's because of the different arrangements, that magnetic quantum number, that you can find P orbitals in 3 different arrangements or D orbitals in 5 different arrangements. So that's where this all comes from. The crazy thing is that some orbitals have higher energies than you'd expect. So sometimes you're going to be filling part of shell or energy level 4 before you fill the sublevel D for level 3. So this is the overall scheme. So if I start to fill this, I'm going to fill with the electron spin considered. So it's going to be up spin and then down spin. And then when I hit the p orbital, I'm going to put up spin first and then down spin. So filling one energy level at a time, 1 electron per orbital until there's 1 in each. And then, so here's where I have to fill the 3d orbital, but after the 4s orbital. Then I fill 4p. Then 5s. And so on and so forth. And so I'm going to speed this up. Again, notice we're filling 1 subshell at a time. So how are you ever going to remember this in order? Well, first of all, for biology, you don't have to know a lot of it. But you can use this diagonal rule, where if you follow these lines, that actually gives you the order that you're filling. And then p orbitals will always have 3 spaces, d orbitals will always have 5, and so on. Now luckily, you're not going to need the diagonal rule much for biology, because we're dealing only in s and p orbitals, but all of this entire lesson has been leading up to this moment, because this is when chemistry gets really exciting for me, because there's a visible pattern now. So watch as I fill these orbitals and look at the periodic table. So hydrogen, 1 electron, that's going to go into the lowest energy state first, so 1s. Then helium, that second electron, fills the rest of the 1s orbital. And then we bump down a row on the periodic table, and here we go, starting to fill 2. 2s up for lithium, 2s downspin for beryllium. Then we jump over to boron, start filling the 2p orbitals. Upspin for boron, upspin for carbon, nitrogen. Then with oxygen. Alright, so now you can see those two open spaces, and you're going to notice that oxygen, just like an H2O, always makes, or tends to make, two bonds. Two hydrogens, two bonds, two open spaces. There's a pattern. Fluorine, neon, shell 2 is full. Starting in shell 3, sodium, magnesium. Jumping over to aluminum, silicon, phosphorus, sulfur. Starting those downspins, chlorine and argon. Full again. 8 and 8. And then I told you we go up to 20. So potassium, calcium. Still dealing only in s and p orbitals. But you're seeing these 8s, something we call the octet rule. That when you're dealing with atoms with low atomic numbers, they do tend to fill that outermost valence shell with only 8 electrons, and this is why. So now you've got the basics of what you learned in middle school, plus the underlying assumptions. Some of them explained, some of them I'm leaving for your physics and chemistry teachers, but this is the foundation of chemistry and atomic behavior. All right, see you next time.